All right, as usual, please remember you can pause at any time and make sure you're taking lots of notes. You can fast forward and rewind as much as you like. This is your video, so go ahead and do it. Let's get started. We're talking about 6 different forms of energy, and today we're talking about light. Get your pencil and notebook ready, please. Learning goal number 2, I know common sources of light energy, and that light can reflect, bend, and can be absorbed. Go ahead and copy your learning goal. Put a scale score in the first box. Press pause so you can copy that down, and when you're done, hit play. Alright, you should have copied down your learning goal and gave yourself a scale score. Let's go ahead and get started. Here's what you need to know about light. Light can travel through space. There's nothing in space. It's empty. There's no matter, but light can still travel through it. Light can also travel through solids like windows. Light can travel through liquids like water. And light can travel through gases like the air in this room. The light's traveling through it right now. But here's what you got to remember. When light travels at different speeds, light travels at different speeds through each type of material, and it can also bounce and be absorbed. So take a look at this glass here. Here's an example of light traveling at different speeds. The pencil looks like it's broken. Here's an example of light reflecting. It's bouncing off. It makes a mirror image. There's 2 mountains. And there's not really a picture for absorb, so I put a sponge since that absorbs things. What you need to know, light can bend. It's called refraction. Make sure you're taking notes at this point. Make sure you press pause to copy this down. Refraction is bend. When light passes from the air to the water, it slows down, causing the light to bend. Take a look at this pencil. It's in the water, but it looks like it's broken. That's because the light is traveling faster through the air, and when it hits the water, it slows down, causing the light to bend, giving you this optical illusion.
This magnifying glass is making my eye look big. Now, why is that? Please consider the following. When light enters something like air, water, glass, or plastic, it slows down a little. And when it slows down, it changes direction. See how one eye is lower than the other? See? Take a look at this. Here are 3 straight beams of light. When they go into the piece of plastic straight, they come out straight. But if the plastic is tilted, the beams of light get tilted. See, they change direction, so they come out this side offset. Now, what would happen if the piece of plastic didn't have straight sides, but had a curved side, like a magnifying glass? Well, the light would change direction, right? Because the surface of the plastic is curved, each beam of light enters the piece of plastic at a slightly different angle, and it changes direction a slightly different amount. Look, over here the beams of light come together at a single point. This is called the focal point. Now what about the magnifying glass? Well, suppose your eye were over here, and light from the room were bouncing off of your eye and going through the piece of plastic this way. Well then, the small area at this end would be spread out over a large area on this side. Your eye would be magnified. Thanks for joining me. I consider the following. By the science guy.
Okay, so there's another example of light refraction. It's when light bends. Let's go ahead on. Reflection is just reflect, which means bounce. Think of a mirror. This cat is taking a drink from a pond with the smooth water, and it's reflecting his image. When you get dressed in the morning and look in the mirror and you see yourself, that's a reflection. That happens when light strikes a smooth, flat surface. It will bounce back in the same pattern, causing a reflection.
When we see objects in a mirror, We're looking at light that's bouncing off the object, and bouncing off the mirror, and then coming into our eyes. Here's the thing. Parts of the object that are on the object's right stay on the right. Parts of the object that are on the object's left stay on the left. It's a mirror image, for crying out loud. See, we're facing the reflection, not the object. So that's why we have echolipsis. Echolipsis.
Hi, I'm Penn, and this is my partner, Charlie. We're Penn and Charlie. Did you ever, I don't know, look at yourself in a spoon? Well, if you look at yourself this way, you're right side up. But if you look at yourself this way, you flip upside down. Why is that? Well, let's look at the spoon sideways. See, the upside down way, the light waves come in, bounce, and cross themselves, making you look upside down. See?
When light bounces off of a flat mirror, it bounces off at the same angle that it hits. In fact, that's what light does with any mirror. But if the mirror is curved, it's making a slightly different angle with the mirror at different places. So it looks weird. Like, totally weird, man. Like, you can, like, totally, like, freak out. Whoa!
Are you taking notes? You better be writing something down in your notebook. Let's keep going. The last thing you need to know about light is that light can be absorbed. When light strikes an object, some of the light is absorbed. This is where we get color from. Let's watch this video and I'll explain some more.
Did you know that white light is a mixture of all the colors of the rainbow? Red light can make you stop. Green light can make you go. The other colors can make you disco. Little by the science guy. Little by the science guy. Science rules. Did you know that white light is a mixture of all the colors of the rainbow? It is. White light's hitting this basketball, but all we see is orange. And white light's hitting this blue gelatin dessert, but all we see is blue gelatin. Now my coat, well, it's got lots of colors. Hey, it's the show about light and color. Now without different colors of light, we couldn't see different colored things. And of course without light, well, we couldn't have a TV show. Oh, funny. Oh, very funny. You can turn the lights on now. Turn the lights on. Sorry. I got it. Now this is the plastic water-filled prism of science. And shining into it is a bright white light. Now when white light goes into a prism, it breaks up into all the colors of the rainbow, what we call the full spectrum of colors. So down here is the spectrum being made by the prism of science. See, here are all the colors of the rainbow. Red, orange, yellow, green, blue, indigo, and purple or violet. Now watch. I'm going to try to break these colors up using another prism. Red, yellow, green, blue, and violet. See, they can't be broken up anymore. What that means is, these are pure colors. White light is a mixture of all the colors of the spectrum, but each color is its own color. White light is colorful. What gives fruits and vegetables all their different colors?
I don't know.
Well, chemicals in the skin of the fruit and vegetable absorb and reflect different wavelengths of light. Take this orange. It's absorbing all the colors of light except orange, which it's reflecting. This green apple, it's reflecting green, absorbing the other colors. The red pepper, it's reflecting red and absorbing the other colors except red. That's the noise. struggle. Gotta get these colors flying. Oh yeah, sure, there it is. Sure. Look at all those colors. It's chemicals reflecting and absorbing white light from the sun. What a party! What a party! Consider the following. There's an old saying in science. We don't see things. We see light bouncing off of things. So when you see my tie, you're seeing light from the lab that hits the tie and goes into the camera and works its way to your eye. Now, here in the lab, we have almost perfectly white light. We have almost all the colors of the spectrum. But when you look at my tie, it looks black with just a few brightly colored spots. What's happening to all the other colors? Where are they going?
I don't know.
Well, they're getting absorbed and turning into heat. You may have noticed this. In a bright light or in the sun, a black cloth feels slightly warmer, than a white cloth. That's because the black cloth is absorbing almost all the colors of light that hit it and changing them to heat, whereas the white cloth is reflecting almost all the colors. This is how paint works. Paint absorbs light. Paint has little particles in it.
Now that's absorption. That's why my shirt appears blue, because white light has all the colors in it. When the light hits my shirt, all the colors are absorbed except for one, light blue, bounces back, and that's what you see. So here's your to-do list for today. I want you to get onto DE, and I want you to log in and find the fundamental called sound, heat, and light. But I just want you to focus on the light part. Don't worry about the heat and the sound. Then I want to make sure you look at the glossary term for light, and there's one for light energy. Use all that information, and you're always welcome to use more reading passages, other videos, other glossary terms, as much as you want. But make sure you hit those three things. And then I want to know, define light energy. What does that mean in your words? I don't want you to copy the definition. And then I want you to give me 2 examples from your world, your day-to-day life. Where do you see light? If you have any questions, raise your hand. If not, go ahead and get to work.